So this time we are going to talk about language models. This one is the next, the next problem that they solve with neural networks. Not necessarily, but in order to be able to explain things gradually in levels of complexity, I think it is the best one to explain next. And then we will also introduce the recursive neural networks, which are now used mostly everywhere. Okay, well, I won't go through the structure of the course again because this is just continuing the previous lecture. Simply now we are going to, so in lecture 12, we finished before the name entity recognition. In lecture 12 or lecture NLP 4, we are going to be talking mostly about language modeling, leaving the more fancy gradient models for the next lecture. Okay, so what is this problem of language modeling? So what do we want to solve here? So the task that we want to solve is that given a piece of text, how can you predict what is going to be the next word that appears in the text? That's something that for humans is very easy, like most AI tasks as usual, but for a computer it is not really easy to do it. If you like statistics, then you will describe it in this way. So what the language model is trying to reproduce or approximate is what are the probabilities of all the possible next words. So what is the probability of this being a book? What's the probability of this being a laptop, an exam, whatever? Depending on all the words that we had before. So how do we do it? So we will have the sequence of words, then which are W1, W2, W3, up to step T. We are just now on step T. Once we are in step T, we want to predict the next word in step T plus 1. What we do first is to translate each one of these words into a vector representation, which are x1, x2, x whatever. The vector representations are at the beginning, or you can understand them as one-hot representations, or you can directly go to understand them as embedding representations in a dense space. And the direct application that they have is not extremely useful. So the direct application that they have is that when you are writing, for instance, typing in your phone or anything, they are able to predict in advance to you typing it what is the next word that you are going to write, and then that allows you to select it quicker. Google is one of the cases, as always, that uses this technology. They use much more sophisticated methods than the one that I am going to explain today. So the method used by Google is the one that I am going to explain in a couple of lectures. This one, the method I will explain now, is the first part of the one that Google uses. The first more advanced method that they develop in neural networks to solve this problem. And then if you build a couple of layers of complexity on that, you end up with the model that Google uses. And then you can use it to predict what is the query that you are going to use in Google in advance. So that's not big deal. It is not extremely useful. But the thing that is really useful of a language model is that, interestingly, once you have solved this problem, which is a proxy of solving the problem of what is the probability of every word given everything that goes before, once you have solved that problem, you have created a very good vector representation or numerical representation of what is happening in all these parts of the sentence. So you have written a very good representation of that part of the equation, of all the different words that come before. And you can use that vector representation for many other NLP tasks. The other very good thing is the method itself, the neural network architecture. Because if you have a neural network architecture that solves this problem very well, you can change the top layer of the neural network and use it for something totally different, like name entity recognition, text classification, and so on. It is a bit, so what is happening in this neural network is a bit like what was happening to our brains when we were kids and we were solving these grammar problems where they give us a sentence and they eliminate one word. And we have to figure out what is that word. I guess that in your countries they were doing the same, because in Spain they really love those problems, and we had to do many of them. Okay, so how do you solve it? What if I am going to go very briefly through the old technology to show you all the struggles that the previous generation of machine learning had to go through to be able to try to solve this problem. And also because they are still used in some situations, and maybe in the future a combination of these methods and the neural networks will work even better than simply neural networks. Or some genius will find a twist to this thing and it will work by itself better than neural networks. For now it doesn't, but well. So what you do is you go by brute force and you computationally represent what is the probability of a word of a given output, given all the outputs, all the inputs of the previous word. Here now I realize this is quite silly. Is this equal to this? No, I am doing it well. And what you do is, rather than represent the probability of one word given all the previous ones, which will be untractable, you only represent the probability of the next word given the few earlier words. So if you remember, in name entity recognition, we were able to solve the problem more or less well by getting as inputs a few of the words, a window of words around the output, around the word that we had to classify. Here it is the same concept. So you want to figure out what is the next word, then get as input the prior context of that word, which are simply n previous words of the output. And then, depending on how big your probability or your model is, you might use a unigram, which what it does is simply represent the probability of every word. So this is going, if the most common word in English is I or an, then if you use this one to generate text, it is going to produce an, because that's always the most likely word. Then later you have bigrams, which represent what is the probability of every couple of words. What is the probability that these two appear together, the probability that these two appear together, and so on. 3 grams, they do it with 3 words. 4 grams do it with 4 words, and so on. And okay, so how do you calculate this probability given a finite amount of data? So the only thing that you do is to apply the very rule of conditional probability. This is the definition of conditional probability. Given the probability of A given B is simply the probability of the intersection divided by B, and that's it. And if you use that rule to calculate this probability in a frequentist setup, then you simply count how many times the next window appears just after the window of input words, divided by how often the window words appear in the universe or in your data set. In our example, this will result in the count of students open their whatever, being that whatever any of the possible options of the next word, divided by the count of students open their. And that's it. If you put here books, this will be count of students open their books divided by students open theirs, nothing. And then if that happens very, very often, then the probability of that combination is going to be larger, and then the language model is going to select books as the next word. But then this has a number of problems. Let's see how am I doing with time. Yeah, okay. This has a number of problems which emerge very quickly. So the first one is that when you are calculating the probabilities in that way, the calculation is to fine grain. So as soon as you don't have in your corpus you don't have any time these combinations of words appears, or the combination of students open their W, if that never appears in your corpus, that probability is going to be 0. But that doesn't mean that as you keep seeing more more text in your testing phase, that doesn't mean that that will never appear. Other problem that you have is with undefined probability. So actually, the problem is not only when the numerator of the equation doesn't show up, but it is also if the denominator doesn't show up, or if the previous window of words never appear in the data set, then the probability becomes 0 divided by 0, which has no solution. And then other one is storage. So if you have how many words in English? 150,000. If you want to be a bit generous, then actually this probability matrix is going to be extremely large, because you need to have many as combinations of words. So there is no way you are going to be able to capture that. And then sparsity. Sparsity is a combination of these two previous problems. So if you have that very, very large matrix of the probability of words given windows of words, then it is going to be full of zeros and undefined entries, which don't mean that actually the probability of that combination is 0. So to be able to solve this problem, then we go. This is a bit strange. I thought that because there are a number of tricks that are able to solve these problems, ameliorate it a little bit. So the way that we use to be able to advance a bit in this problem is, as before, the neural network approach, because it is able to use a much smaller matrix to be able to represent the probabilities of all of the next word given the previous ones, and it doesn't need to store so much space, and it will not have the sparsity problem, because once you define an input space with the neural network, then every point in this space is actually well defined. And how do we do it with a neural network in our attempts to be able to solve the problems of the n-gram? So we do, for now, to make the explanation a bit gradual, we are going to use, or one way you can try to solve it is to use very much the same architecture that we were using before for the name entity recognition. This is exactly as before. You have as input a number of words that you concatenate, then you apply a layer of the neural network with a nonlinearity, you get another hidden state of activity of neurons, apply other matrix, and then in the output you are going to get the probability of each one of the possible each one of the possible words. What is the probability that each word in the vocabulary is going to be the next one in the sentence? So this is exactly like the neural network that we have for name entity recognition, but we have changed the top layer from one single output to as many outputs as words in the vocabulary. If we write the equations for this one, they are very similar to the name entity recognition, so we get all the previous words, we concatenate them, we transform these one-hot representations into embeddings, which are part of the R for E space. So E, this uppercase E, is the number of embedding dimensions in your skip-gram model or whatever you use to create these embeddings. Then later, all this concatenation E goes to the nonlinear, well, not nonlinear, but to the first layer of the neural network. Then you send that one to the next layer, and here it is where it is a little bit different from the name entity recognition, because rather than having only this as an output, we are also adding a baseline, which is not too important, but what is important is that we are having the softmax. And remember that the softmax, we already use it in the skip-gram and the word-to-vec problem. So the advantage of this is that we have got completely rid of the sparsity problem. Then we don't need to store all combinations of words, because the neural network is able to interpolate between the probabilities of combinations of words that are quite similar to each other but not exactly the same. But then there are a number of remaining problems. These are problems that we also had in the n-gram model, but here they still remain. But in the n-gram models, the other problems were so big that we are not thinking about this. So the first problem we have is that for the input, we are only considering a window of words. We are only considering n previous words. And the larger we create this window, the larger this W becomes, and then after some point we start getting again into the sparsity problem that we had in the n-gram definition. In the n-gram definition, we will get sparsity problems as soon as we have a 3 n-gram or a 4 gram, but here we get the sparsity problem later on, which is an advantage. So, okay, as I said, the size of W increases as the window becomes larger, and then there is a problem or something that your intuition will tell you that is a problem, and is that you are not treating every one of the input words in the same way. You are actually treating each one completely different. And the reason for this is that this W, so this W is going to have as many rows as the units in the next layer, as many columns as words in the windows, multiplied by the number of embeddings, number of embedding dimensions of each input. And that W matrix is divided in columns, or in macro columns, let's say. So the first 4 columns, the weights of those first 4 columns are going, let me think. No. These are the weights of the first 4 columns are coding for how the embedding of this first word impacts on the internal representation. The next 4 columns of W are coding for how the second word impacts on the internal representation and on the probabilities. So if you suddenly get this input and you swap words, well, no, that doesn't make sense. Forget about that. So anyway, every word is treated completely differently, when in reality words are actually should be processed more or less in the same way, our intuition will tell us. So how do we solve those problems? So we go to the next, a bit more advanced, more sophisticated architecture, which is called the recursive neural network. And what the recursive neural network does is that rather than having a simple fit for words architecture that gets all the words in one go, we get an architecture that gets a single word, but this architecture has an extra output that feeds to itself, such that the architecture can read one word after another. So conceptually, this is what it will do. Before, what we were doing is simply eliminating everything that was happening before, focusing on the window, and we process that in a single step. In the recursive neural network, we'll go one word at a time, and we do some operations with the embedding representation of the word, and in every step, we accumulate a something representation of the input. And this will be the equations. Now we have a single word. The representation of the word is multiplied by a weight, so this is the standard layer of the neural network. But then we have a extra input. So this is a neural network where we are concatenating the embedding representation of a word with an h of t-1. And h of t-1 is simply this value or the activity of the internal neurons of the recursive neural network, but the activities of the first step, the activity that those neurons got when we were processing the first word. So at the beginning, this will be like only and the internal layer is going to have as an input the embedding of that word, and also as an input a linear transformation of some initial values that we define for words outside the window. And then we apply it over and over, one after another, and in the last step, we apply the last layer, which will tell us what are the probabilities of each one of the possible next words. And the good thing is that as you apply this, one good thing is that you don't have limit of a window, because you can go as far in time as possible. Every time that you kind of digest a number of words, you already have an output of what is going to be the next word. And so you can actually solve the whole problem by eliminating the window, as I said before. Then the size of W does not increase when you try to digest more and more words, because the size of W only depends on the size of the embedding. If we go to the previous equations, oh, here I didn't put, but yeah, anyway. In other equations that they have, I use that funny nomenclature where we have the number of dimensions of each one of the vectors and matrices inside the equation. Here I try to portray the dimensions with these belong to R to the space R to the power of whatever. So the input is simply E, the output becomes larger because you are, well, larger, not necessarily. It becomes smaller indeed, often. It is the input of that non-linearity what becomes larger. So this W weight always has as many columns as the number of embeddings, and then as many outputs as the number of units that you want to put in the second layer. So that doesn't grow. And then there are a couple of new problems, which are that the training this type of architecture is a bit slow for a reason that I will explain later when we see how to do backpropagation here. And also a strong problem in the recursive neural network that other architectures solve is that although you can digest many words, in the end, the effect that words that are a little bit far away in time, the effect that those words have in the output actually disappears because of a mathematical property of the backpropagation algorithm. Okay, and now, how do we learn this model? Well, we learn it very much like we have been doing with name entity recognition and like we have been doing with the word-to-vec problem. We apply we get a big corpus, we represent every word with a vector in space, but then we start to change some parts. So you have a model which is not a feed-forward neural network anymore, it is a recursive one, so that's a little chain from what we were doing before, and it tries to predict a vector of a word, the vector of the next word, given all the words that are not really around it, but rather before, so that's another small chain. And then the probability that we are trying to approximate is that one, which I already was talking about before. The way to train it is exactly the same as before. We go through each word, we modify the neural network a little bit for it to minimize the loss function a bit better, and then we repeat the other two steps over and over again. Okay, and now what is the loss function that we have to use here? So again, here I will introduce another small innovation that was used in the recursive neural networks. So if you remember from word-to-vec in CBOW, we were trying to minimize this equation. So we were trying to make we made an error function that was trying to optimize or make the dot product or the projection of the word that was in the center, given the words in the context, as good as possible, so as high as possible, while minimizing the vector, the dot product projection when the words were from a noise distribution. Here I am again using the nomenclature that I am introducing. If you think the nomenclature is not too useful, then do let me know. So what the brackets mean is that the thing inside the brackets is a matrix or a vector, and then underneath the matrix or the vectors you have in upper cases what are the dimensions of the vector or the matrix. If there is only one letter, this means that this is a vector with as many elements as V, then and then this will be the same. But the same nomenclature applies to the specific case of what we were doing in the word-to-vec example. Then, so this was the loss function that we were using in word-to-vec. Then in GLOW we were using another a bit more exotic error function, which the authors were trying to argue in terms with some equations, but in reality it is mostly heuristic. So we have a ramp function of the count of how often one word appears next to another, or how often two words appear in the context of each other. And then we have a linear representation, or we want the dot product or the projection of the embedding representations of the two words that appear in the context to be as close as possible as the logarithm of the count of how often they appear in the context of each other. Here, using the funny nomenclature, we start having, when we have several numbers or several uppercase variables underneath a bracket, it means those are the dimensions of the matrix, so V rows and V columns. Then in name entity recognition, we had yet another error function, which was the margin loss, and that one simply is trying to make the difference between these two outputs at least 1 point different from each other. And then now we introduce yet another error function, which is the cross entropy loss. So what the cross entropy loss does is to try to minimize what is the dot product, try to minimize the dot product between, or actually tries to maximize the dot product between the output that the neural network should have. So the classification, these are one-hot representations, remember? So the classification of the word that should be in the output of the neural network multiplied by the logarithm of the output that the neural network is actually showing. However, remember that in X we are using one-hot representations. So, and given that this is a vector of V elements, this will result in a matrix where all the elements of V, all the elements of the vector actually disappear, except for the element of X that was actually a 1. So in the end, we are going to have simply that logarithm. Indeed, well, here it is correct. So we are going to have the logarithm of the element number I of the output of the neural network. So, and the reason why at the beginning it might be a bit surprising why that actually works, but what is doing the magic there is the logarithm, because the logarithm, if you represent it in the xy space, so this will be x, and this will be y, not the xy that we have in that equation, but it looks like this. So you will say, well, but that's not making sense, because then if this is positive, so if later you apply to the negative, we are actually not trying to go in the correct direction of the error function. The reason why it works is that actually all the outputs of the softmax are below 1. So in reality, the part of the sigmoid, the part of the logarithm that we are using is this one. And that part of the logarithm, what it is doing is that we have there x of I. So if I is the output that the neural network should be using, or I is the word that the neural network should be selecting, if that word is having a probability close to 1, then the loss is quite small, no big deal. But as the more the probability of the correct word is approaching to 0, then the larger and larger error that we are going to have because of that word. And that error goes to infinity. So if that probability is almost 0, you are going to have an incredibly large error. And then that error seems to work very well in the softmax cases. Okay, so how do we apply that? How do we apply backpropagation here? So then, or what is actually the meaning of the loss? So the loss of the first, in the first step, so it will be, this is a bit a different nomenclature. So J of step 1, given all the parameters of the neural network, which are theta, that will mean the error or the negative probability, which is, it is simply if you use the probabilistic nomenclature, it is the error of getting the next word correct or right, or the negative log probability of the next word. Then the next one is again the error for getting given the input these students. It will be the error for the next word where the correct one is open. Then the next one will be yet for the next word. Given the input the students open, what is the error of getting their correct or not, and the next one will be the same. And then you apply, it is exactly the same property in all the following words. And given a data set or given a very long text, the actual loss that you are trying to minimize is the summation of all those different, of the loss that you are getting in every step. So when you apply backpropagation actually to that summation of the total loss. But that will be the theoretical way. The ideal way you will do it. You will calculate the loss given all the words in your corpus, and then you apply backpropagation to update the weights a little bit. But in reality, what we do is what is called mini-batch learning. So we don't do it over the whole data set. We actually do it on sections of the data set or sentences, individual sentences from the data set. And then to be able to apply backpropagation, because so far we have only applied backpropagation to feed-forward neural networks. To be able to apply to a recursive neural network, what we do is actually backpropagation through time. So usually here it is not so confusing because I have been unfolding the recursive neural network in time, in all the previous pictures, but usually what people do is to only show a single the total architecture of the neural network with an output that feeds to itself. But then if you unroll that architecture in time, you are going to get something like this. And then to apply backpropagation, you simply apply the chain rule to this equation, because actually, again, because of the way the derivatives propagate in a neural network, the derivative of j given the intermediate weights is equal to the summation of the derivative of the loss given each one of the intermediate weights. And the reason why it is a summation is from one of the rules of how to send the gradient through a neural network. This was, if you remember, these were two of the examples, two of the rules for backpropagation that we were explaining before. One is for what do we do when two branches of a neural network bifurcate, and what do we do when two branches of the neural network get together again. And what we do is simply, if you apply the chain rule, so the way to express this bifurcation of branches is through this equation. So you will have that the function, the transfer function of the next layer is actually equal to, it is a function of those two branches, and each one of those branches, if they are coming from the same, or they depend on the same variable, then each one of them is going to be a function of t. And if you apply the chain rule there, you are going to get something like this. So you are going to actually get a summation of the derivative in each one of the branches independently. And if we look at our neural network, actually the loss that we have at the output is a function of all these intermediate weights. So that's a bifurcation of the neural network through many other branches. But then the weight that we have in each step of the neural network is actually the same, because remember that we are feeding the neural networks to itself. So in every step we are applying exactly the same weight matrix. So in the equation, if we apply that equation, the chain rule to the total loss, we are going to get a huge summation, but because the derivative of WH in step Y is with respect to the derivative of the global or the main matrix is always equal to 1, because they are actually the same, then that disappears, and you end up having that the derivative of the total sum of the loss is equal to simply the summation of all the different of the loss in each one of the steps. If we represent it graphically, it will be like this. Once we get that gradient, if we use the backpropagation algorithm after applying the chain rule, then the gradient is going to be backpropagated back in time through all the different steps of the recursive neural network when we unfold the neural network in time. Yeah, and then that's something, once we have had this neural network trained and it works very well and so on, we can use it for our or we can use it because it is predicting what is the probability of the next word. We can actually use it to generate text. Like if you have been following a bit the news in previous year, they made a very big marketing splash with the GTP2 model because they said that it was able to reproduce human speech so good that it could be used by cybercrime and so on. In reality, they don't work so extremely good, but it is interesting to see because they get kind of close there. For instance, if you get a recursive neural network like this one and you train it on a lot of speeches of Obama, and then you apply it in reverse, and what you do is to start generating, you generate a first random word, and then you send that word to your recursive neural network, and the recursive neural network will say which is the most likely next word. Then you grab that word, put it in the input, send it to the neural network again, the two first words that you have, calculate what is the best probability of the third word, put it in the input, and keep doing that over and over again. You get something like this, which if you pay a bit of attention, it doesn't make much sense. But it is quite surprising that a machine is actually able to do something that, at least in a short time frame, it still makes a little bit of sense. And then you can do it with other setup. For instance, if you get all the scripts of Harry Potter, it is going to generate the text that you have there underneath. So again, it represents a bit the style of the book, but also it doesn't really mean stuff. You could have a try, but if you write Harry Potter 8 with this, probably you won't get very, very far. And you can also do it with everything, with any, not only with text, but with any sequence of elements where the probabilities of an element has some relationship or is causally defined by what was the sequence that precedes it in time. So another funny experiment that they did is that you can feed a neural network one color or train a neural network on predicting what is going to be the fancy name and the RGB values of a given color, using as first input simply the color itself. The surprising thing, you might say, well, this is not too impressive, but the impressive thing of this is that the neural network is working at the character level. So the neural network, rather than using an embedding for each word, it is using an embedding for each character. So it is able to make sensible words, even when it is generating one character at a time. So this neural network actually hasn't got any internal numerical representation of full words, but only of characters. And there are actually people that earn money, they work in their life simply creating these funny colors. But here you have a neural network that does it automatically, not so fancy, but it kind of does it. What else? How am I doing with time? Yeah. And how do we evaluate the language model? So in all the previous lectures, we always had a method to evaluate our model, how good our model is doing. So what you do is calculate something called perplexity, which its meaning, or what it tries to capture, is how surprised the neural network is of finding the next word. So if the neural network is thinking that the next word is going to be books, but actually it is laptops, then it might not be too surprised because, okay, the neural network was giving the maximum probability to books, but the probability that it was giving to laptops was also more or less high. Not as high as books, but the output in the softmax was getting close by. But if the output is actually, I don't know, like plane or car or cat, then if the probability that the neural network was giving to cat was extremely low, the neural network is going to get very surprised, so to speak. So writing it numerically, the way we express perplexity is 1 divided by the probability that the recursive neural network was giving to the next word, given all the previous words that we have. If this probability is very high, then this fraction is going to be very small, so the perplexity is going to be low. If the probability that the neural network was giving to the actual word was very low, then this division is going to become very high, and that's going to become the perplexity very high. This product, what it means is that we multiply this probability for each one of the steps. So we multiply it for t equal to 1, so it will be the first step, t equal to 2, the second step when you read the output. So we actually calculate kind of the average. Well, not really the average, but in probabilistic terms, it is conceptually the same than the average or the joint probability of all the different steps. And the way we calculate the probability is simply, well, we do the same dot product than before. We get the one hot representation of the real world by the one hot or the softmax output of the neural network, and that's going to give us the value that the neural network was having in the softmax. So if we go to the previous diagram, oh man, that's quite far away. So it will be, we are having in the end 1 divided, if the output, the real world was books, we are having this 1 divided by this number. If the real world that the neural network finds in the corpus is cat, we are going to have 1 divided by this tiny number, and that's going to become very large. A property of the softmax, which is shared with the property of the definition of probability, is that if you sum up all these outputs, they are going to be exactly equal to 1. Or they try to be exactly equal to 1. Let's go. Yeah. And then, well, I was forgetting that you actually do this. You get it to the power of 1 divided by t. Yeah, and something quite interesting of this equation of perplexity is that it is very symmetric, very similar to the loss function that we were using. And if you do a couple of modifications, the key thing that you do here is that you apply the logarithm to the whole equation and then apply the exponential. So this is a typical trick in mathematics. It is like if you divide a number by 10 and then multiply by 10. You are simply applying an operation and then the inverse of the operation. So you should obtain exactly the same value as before. If you get any number in the universe, well, not any, because logarithm is not defined for negative numbers, but if you apply, it's not, well, anyway, if you apply the logarithm to a number and then apply the exponential, you should get again the same number, at least with positive elements. But what happens here is that actually this logarithm is the equation that we were having before for the loss. Where is the loss? The loss is lost. Well, anyway, yeah, that's the equation. If you see, it is the logarithm of simply the correct output. Yeah. So actually the perplexity is simply the exponential of the loss. So this indicates that that we are getting, so we have got to the same equation through 2 different lines of thought, which is a good sign when you are doing statistics and so on. So it means that from the probabilistic point of view, the loss that we have chosen before is actually quite sensible. Okay, and then some examples of measuring the quality of language models. So this is some review, well, not a review, but a method or a version of language models that they published time ago, and then they calculate perplexity for a number of alternative architectures. And then if you order this in time, you realize that as we get more and more complex recursive neural networks, we end up having lower and lower perplexity, which means that the neural network is less and less impressed by the next word. It is able to predict them better. At the beginning, they were simply, so they interpolated, that was simply an engram or a neural network like the very first that we were having that concatenates embeddings. Then we started having recursive neural networks where the internal layer was 1,000 and something. If you make a larger internal layer, surprisingly here the perplexity increases, probably because this one started to overfit the data. I don't know why they got accepted when they were so worse, but anyway. And then later you start introducing more things. Here you start seeing 2016 the LSTMs start to get spread, and in the next lecture we will explain what is LSTM. Then here we are saying, oh look, our amazing neural networks are doing even better. Oh, not really, this one was better. Well, anyway, they were showing off another type of of more sophisticated neural network. And then if we update this table, we will have more rows with the newer ones, like the bidirectional LSTMs, the GRU architecture, the Elmo model, the ULMN fit, then the BERT, then GP2, and so on. But in a couple of lectures, we will start talking about those. And then once you have it, the very important thing is that the task in itself, as I said, is not very important, the task of predicting the next word, but then you can use, once you have the internal representation that your language model produces and the architecture of a language model that works very well, you can use it for many other downstream tasks, like predictive typing, which is the simplest one, but then you can also recognize speech. So when you are trying to recognize the speech of a person, if you are able to predict imagine that you are talking with the telephone and the telephone is trying to transcribe what you are talking into text. If you are able to predict what is the next word, then the number of possible, the number of candidates words is much smaller, so you are able to allocate what is the most likely word that you are going to actually speak a couple of seconds later. Handwriting recognition as well, because you can also model exactly the same example with the speech, because you can predict where the person is going to move next or what is the next word. Also grammar correction, if you see, and this is working now everywhere in Google Documents and in any other sensible word processor. Classified text, well, for anything. Machine translation, which is an example that we will see later. You can also use it for the name entity recognition. So this is an example where before, in the previous lecture, we were designing an architecture exactly that can only be used for name entity recognition. But the very good thing of language models is that once they are working very well on predicting the next word, you can change simply the top layer of the language model and you can reuse it for anything else. You train the language model on a lot of text simply to predict the next word, and then you change the top layer, use the weights that you have obtained after training the next word in a lot of text. You simply reinitialize the new top layer, freeze all the weights, all the order weights, and then you train the top layer in a data set for your new tasks, like name entity recognition. And this tends to work surprisingly well. This one is another very typical case that before, I guess that they are still doing it today, but before they were working very hard on this problem, which is text classification. I think they were working very hard because it was very easy to get a corpus, a training set, because you simply go to the Internet Movie Database or to maybe in Facebook. No, Internet Movie Database was the best one, I think, because every person will write a little sentence saying if they like the movie or not, and then later will give a score to the movie. So actually they are creating, those many users across the world are creating a very large label data set. And what you can use the language model for is on trying to predict what is the score they gave to the movie, reading only what they wrote in the feedback that they gave to the movie database. And it was quite a difficult problem, or a bit interesting problem, because while many people write quite straight sentences, there were many others that were a bit sarcastic, and if you start reading the sentence, it seems that they are talking positively of the movie, but then with a couple of words at the very end, suddenly the meaning of the sentence or the classification of the sentence totally changes. If you say, I thought that I was going to see an amazing movie of spaceship battles and blah blah blah, but in the end this was not the case, and I was very disappointed. So suddenly with the final two words, the feeling of the sentence completely reverses. Other one is, well, another classification to see what is actually the language of a piece of text. You do exactly the same. You apply the language model, but then you change the top layer. Rather than trying to predict the probability of the next word, you change the top layer with a single output that tries to predict whether the text is German, English, Korean, well, Korean maybe not, but any of the Latin script languages. And that was so far for today. I have finished a bit early. I think that in the next lectures I will be able to introduce a bit more of material. I was trying to be a bit careful here. But in the next lectures we are going to start seeing a bit more complex architectures and more fancy ones, like, well, the ones we were seeing before, or we were seeing today, is what they call the vanilla recursive neural networks, because they are very simple. But then the next lectures we are going to see the GRU and the LSTM, which has an extra twist to be able to solve a problem that backpropagation has when applied to recursive neural networks. It is the problem of vanishing and exploding gradients. Then later we can have recursive neural networks, like those two LSTM and so on, stack one on top of each other, like to make deeper networks. And then later we can have all sorts of combinations like bidirectional, attention, self-attention, residual, and so on. We will be talking about those. We will introduce them gradually during the next lectures. Well, this is again the structure, but you have heard it already a few times. In the next lecture, we are going to talk a bit more about language models, what is the vanishing gradient problem and how it can be solved or it can be ameliorated, then the other fancy ones, and we are also going to go to the next big problem that we try to solve, which is machine translation. Here are some papers, and yeah, that's everything for today. Any question that you have, do let me know. Yeah.
I was wondering if it's in the Obama speech
Yeah.
example, is it difficult to predict when to end a sentence?
Yes.
Does. You just use two sentences of 27 words.
Yes. Yeah. So yes, that's a difficult problem, and there are different ways of trying to solve it. One is simply you have a character that is simply the end of text character, and then you, as soon as your neural network grabs that character, or not that character, that word, the end of text token, you stop the text, or you might introduce some more sophisticated methods, like for instance, what some people do is when the probability of the next word is too random, then they stop it there, or they also introduce into the neural network how many words we have gone through already for the neural network not to talk forever. Or other problem that they often have is that these methods often produce very short sentences. So you could introduce into the loss function a penalization for very short sentences. There are quite a number of tricks. Any other? Okay, so then that's everything for today. Any question, do let me know. Any suggestion of how to make the lectures better, do let me know as well.